Today we want to look at how to take the derivative of a log function. And to do this, we're going to have to use implicit differentiation that we looked at yesterday. Now, first, I want to look at something that we've already talked about, and that was how to take the derivative of 4 to the x. And if you remember, the way we took the derivative of 4 to the x is we rewrote it, we e'd it, so to speak, and we rewrote it as e to the natural log of 4 to the x. We bring that x down in front, and so we take the derivative of e to the natural log of 4 times x, and the derivative of e is e to the junk times the derivative, and all of that stuff. And if you remember, we ended up with the natural log of 4 times 4 to the x. But the important thing I want to remember is how we took this and wrote it like that. Now, what that would mean is if we had the derivative of 5x squared plus 1, the derivative of the outside is the 5x, so that would be the natural log of 5 times 5x squared plus 1 times the derivative of the inside, which would be 2x. So that kind of reviews what we've talked about previously with our chain rule and exponentials. Now let's look at a logarithm. So what we're going to do is we want to find the derivative of natural log. So to do that, what we're going to do is we're going to rewrite this in exponential form. That's e to the y equals x. And now with implicit differentiation, I am going to take the derivative of both sides. So the derivative of e to the y is e to the y times dy dx. Our derivative of x is 1. Now we divide and we get dy dx is equal to 1 over e to the y. But from up top, we know that e to the y is equal to x, so our derivative is 1 over x. So the derivative of natural log is 1 over x. Now, that works because of our e, the derivative of e, and all of that stuff that we talked about previously with natural logs and all that only really works when we're taking the derivative of natural log. If it's a log of a different base, that doesn't work that nicely. So what we're going to have to do is if we have a derivative of anything else, another log base A, common log, for example, or any other log, we're going to rewrite the log base a of x with the change of base formula. And so we can rewrite log base a of x as the natural log of x divided by the natural log of a. Now, we don't really use this change of base formula much anymore because our calculators can now just evaluate log base a of x. But in this case, we need to do it. Now, once we have it written in that form, we're taking the derivative with respect to x, which is just the natural log of a. Because the natural log of a is a constant, we can move it out in front. So we can rewrite this as 1 over the natural log of a times the derivative of natural log, which is 1 over x. And so this is just going to give us 1 over x times the natural log of a. So that's what we have to do anytime we take the derivative of a logarithm other than natural log. Now, because of that, most of what we're going to do is with natural log because we can write it in that form. So let's look at an example. Take the derivative of the natural log of x squared cosine of 3x. Well, first, we take the derivative chain rule of the outside part of natural log. So the derivative is just 1 over the inside part. So the inside by the chain rule, derivative of the outside, inside staying the same, times the derivative of the inside. Now to take the derivative of the inside, we have to use the product rule. Derivative of the first times the second plus the first times derivative of the second, which is minus sine of 3x times the derivative of the inside, which is minus 3. So you notice this derivative of natural log is just 1 over whatever the inside is. If we have the derivative of the log base 3, you could think of this as two ways. One way, if you remember that formula we looked at, we just write this as the natural log over the natural log of 3, which is going to give us 1 over the natural log of 3 times the derivative of natural log, which would be 1 over 4x plus 1, derivative of natural log, inside staying the same, times the derivative of the inside, which is just 4. Now, let's say we want to take the derivative of this. X to the sine of x. So we now have a variable raised to a variable. So this is not our power rule. We just can't bring down the sign. This is not our exponential rule where it just throws natural log out in front. We need to find this some other way. And the way we're going to do this is with implicit differentiation. Okay? But first, what I'm going to do is I'm going to take the natural log of both sides. By taking the natural log of both sides, it allows me to take this exponent and bring it down in front. So this becomes sine of x times natural log of x. Now, if I take the derivative of both sides, the derivative of natural log of y is 1 over y times dy dx. Over here, I have to use a product rule. Derivative of the first is cosine times natural log. I forgot my x there with my cosine. Plus the first, sine of x, times the derivative of my second, which is 1 over x. So now if I solve for dy dx, I multiply by y, and I get cosine of x times natural log of x plus, I'm going to write this as sine of x over x. Now, the last thing I want to do, if we can, especially if we're given something like this that's implicitly, we want to write this with only x's in our answer. So I need to get rid of this y. And I can use my original function as the thing I substitute in. So I can rewrite this as x sine of x, and then I have cosine of x times natural log plus sine of x over x. So there is my derivative. So you're going to have a few homework questions where you need to do this, where you need to, if you have a power to a power like this, or excuse me, an exponent to an exponent, you're going to take the natural log of both sides. I know a little simpler one for your homework is going to be what's the derivative of x to the x. And to do that, you're going to have to do this step of taking the natural log of both sides. Now, we have pretty much taken now the derivative of almost everything we know. Polynomials, trigs, quotient rule, product rule, chain rule. We have our logarithms. We have our inverse trig functions. But a very simple function that we've looked at that we don't know how to take the derivative of is absolute value. How do we take the derivative of absolute value? Now, we know what absolute value looks like. Looks like this. So just from looking at the graph, we can tell over here that dy dx is just 1. It's just a straight line. And over here, dy dx is -1. It's just a straight line. And we get this divide down the middle, right? We got a corner here, so the derivative doesn't even exist at 0. How do we get that here? Well, if you remember way back at the beginning when we talked about absolute value, and we talked about piecewise functions. We would write this as a piecewise function as x when x is greater than or equal to 0, and negative x when x is less than 0. So if we write it as a piecewise function, we can now take the derivative as a piecewise function. And so when our derivative at x, our derivative is just 1. Our derivative at negative x is actually just negative 1. Now, we do have the issue of, is the derivative at 0? No, we got to be careful on that. But here's how, anytime you're dealing with absolute value, the way you are able to find the derivative or solve equations or deal with things with absolute value is you write it as a piecewise function. You even did that way back in Algebra 1 when you solved simple absolute value equations. You would write it as a positive case and as a negative case. You were basically writing it as a piecewise function. So at this point, there's not many functions we don't know how to take the derivative of that we have seen before. There's functions out there we haven't seen that we may not know, but now with all of our rules, we're ready to go to the next step now and kind of say, okay, what can we use our derivative for? What are some of the applications and problems we can solve by using our derivative? And that's what we want to look at next. The homework here, this is 3-6. This homework is also due on Tuesday, December 1st. It's due in the morning by class time if we're in class. If not, it'll be due online at that same time. And make sure once you have watched the video, taken the notes and all of that, that you mark completed on your Otis lesson.